Hello students, in this video we'll begin our discussion of finding Schwarz Christoffel transformations for degenerate polygons that tend to be open, not closed. And in particular, what we'll be able to do is we'll be able to find formulas for the streamlines of flows around various sort of natural regions for a fluid to flow. So let's consider the following region. Consider the ramp shape. So here's the ramp shape we're going to look at. We're going to go like this to a point which I'm going to call I tau. Then we're going to go down over here to the origin. Then we're going to go over this way. So this is our region over here. And we're imagining that we have like a fluid that's in this region, right? So this is our region over here. And this is the real axis. That's the imaginary axis over there, okay? So I want to find the conformal mapping from the upper half space onto this region, right? Let's call this region R for a ramp. So region R. Let's find the Schwarz Christoffel mapping. Okay. And so here's the idea. There's two bends over here, right? There's a bend over here and there's a bend over here. There's two exterior angles, right? So note, there are two vertices. Of this polygon, right? It'd be more clear, right, if this polygon sort of came back and closed itself off, right, went up and then back down over, something like that. But these open degenerate shapes still work with Schwarz Christoffel. I'll explain why. So what we have over here is we have one exterior angle. There's an exterior angle over here, alpha, right? Notice how, of course, this is a non-convex polygon, right? And this polygon is not convex. Like all of our previous examples, triangles, squares, rectangles, all convex, right? This one's a little more complicated. Good, that's alpha, and then there's this angle over here, beta, right? So what do we know about these angles over here? We know that alpha plus 3 pi over 2, that's the interior angle over here, right? That's a 3 pi over 2. Has to equal to pi, because the interior angle plus the exterior angle have to add up to pi, right? And so this gives me a negative, right? This says that alpha is equal to negative pi over 2, which is going to induce a positive exponent in the Schwarz Christoffel transformation, right? This is going to be a positive exponent. Okay, positive exponent. Good. All right, now let's look at the beta. Well, beta plus what? Beta plus the interior angle over here is just pi over 2, right? Pi over 2 has to be equal to pi. So that says that beta is equal to positive pi over 2, right? And now it'll give me a negative exponent, right? So important to keep track of that thing with Schwarz Christoffel. That's a negative exponent. Okay, great. And so now what's the Schwarz Christoffel transformation? Our Schwarz Christoffel transformation now is what? Is f prime of z is some constant over here, a. I'm going to choose my vertex points. I'm going to choose z equals 1 and z equals -1 to be my points that map onto these things. So z equals -1 is going to map to this point over here, and z equals 1 is going to map to the origin over here is a, and now have z plus 1 to what? That's going to be a positive exponent, so 1/2, and then a z minus 1 to the -1/2. Right? Now remember that this derivative over here is going to correspond to the fluid velocity, right? If we're talking about fluid flows. And if I want to find streamlines, I have to find the function f itself, right? So I need to find f, the function f itself, to find the streamlines, right? So we need f of z to find the streamlines. Okay, good. All right, so what's the beautiful thing? The beautiful thing is that if I can find a formula for an antiderivative of this, as I typically would, that formula is going to give me the analytic extension, right? Good. So let's integrate this. So what would f be? F of z. I'm just going to leave it as an indefinite integral. Technically, I'm going to be more precise with this. I have to put limits of integration here. Let me be imprecise first, right? And just to get the right formula, okay? Well, then we're going to have the square root of z plus 1 over z minus 1 dz. Great. Okay, this suggests trig, or hyperbolic trig rather, not trig. So what I'm going to do is the following. I'm going to say that I'm going to turn this into a zeta integral. So this is going to be the integral a and then square root. I'll let z be cosh of zeta plus 1 over cosh of zeta minus 1, and then the derivative of cosh is sinh, so I have sinh of zeta d zeta, like that. Okay, I'll multiply everything by 2. This becomes the integral of the square root of e to the zeta plus e to the negative zeta plus 2 over e to the zeta plus e to the negative zeta minus 2 sinh of the zeta d zeta. Now, of course, what is this? That's a perfect square. That's e to the zeta over 2 plus e to the negative zeta over 2 squared, and that's e to the zeta over 2 minus e to the negative zeta over 2 squared. So that's the hyperbolic cotangent of zeta over 2, right? Good. So this is, of course, just going to be what? This is going to be a times the integral of hyperbolic cotangent squared is just going to be a cotangent of zeta over 2. Double angle formula for sinh is going to be twice the sinh of zeta over 2, the cosh of zeta over 2 d zeta. That's going to be a, the integral. The sinh is going to cancel with all those things in the denominator. It's going to be cosh squared, right? And then 2 of them, right? So I have 2 cosh squared, but cosh squared is 1 plus the cosh of 2h, right? So this is going to be, by double angle formula, 1. So I'm going to have cosh squared, right? And so cosh squared is going to be 1 plus the cosh of twice the angle over 2. But the 2 is going to cancel out. It's going to be 1 plus cosh zeta d zeta. Okay? So this is going to be a times zeta plus the sinh of zeta plus b, right? Good. Now, what is zeta? So zeta, of course, is the cosh. So z is the cosh of theta, right? So z is the cosh of zeta. So the square root of z squared minus 1 is the sinh of zeta, right? Good. Okie doke. And so now what this allows me to do is the following. So now this becomes a z squared minus 1, and this becomes an arc cosh, right? So our solution, so our f of z is going to be a, and then square root of z squared minus 1. And then the arc cosh is well known. That's just the natural log of z plus the square root of z squared minus 1 plus b. Good. So there's our conformal mapping. I need to find a and b, though, right? So, of course, when I plug in -1, what's going to happen? So I know that f of -1 is going to be what? F of -1 has to be I times tau, right? I times tau is f of -1. When I plug in -1 over here, I get a 0. When I plug in -1 over here, I get in the log. This is the actual log, right? The log of -1. The log of -1 is I pi, and that's 0. So this becomes equal to a, and then that's going to be the log of -1 is going to be I pi, right? Let's make sure if I get a negative or not, though. Let's think. So, nope, just a. We'll do the log of 1. So if I plug in a 1, I get a 0, right? So let's do that one too. So f of 0 is going to be what? F of 1 is going to be 0, I'm sorry. So f of 1 is going to be 0. F of 1 is going to be 0, right? And what's f of 1 over here? F of 1 is going to be a 0. That's the log of 1 is going to be 0. And then this is going to be I pi, right? I pi plus b. And so the a is going to be 0, and that's going to be equal to b. So b is equal to 0. Good. So b is equal to 0. And this says that a is what? A is going to be, the i's cancel out. We're going to get a tau over pi. So this says that a is tau over pi. Okay. Good. So our conformal mapping, f of z, is tau over pi, square root of z squared minus 1, plus the log of z plus the square root of z squared minus 1. Okay. Now, how do I use it to find the streamlines? If you replace z with what? With t, that's the real part, plus I, a constant c, right? The imaginary part's constant. For t between -infinity and infinity, those are going to be your streamlines, because the streamlines are the imaginary part of the antiderivative being constant. So if I replace z with t plus ic for a fixed constant c, and I simulate those, I'll get the streamlines of this flow, right? So you're going to have a flow like this. Your streamlines are going to look like, they're not going to hit that corner, obviously, but they're going to go like that, like that, like that, and like that. So your streamlines are going to go over this ramp. The closer you get to this axis over here, the more tightly you go around that ramp, right? So in other words, if you plug these things in, like Desmos or some computer software, you can actually simulate what those curves are going to look like, right? And so of course you're parametrizing, that's like your y value. So it gives you a curve in the complex plane. You can forget about I and just plot that as an x and a y, right? Where your x is equal to t and your y is equal to a constant c. You can find all those streamlines, get beautiful simulations for the fluid flow around this sort of the sharp drop-off ramp. Thank you very much.